Good evening, everyone. Today we will be talking about distributed database systems. So, what are database systems, first of all? So, distributed database systems are those which span across multiple locations to provide high performance and availability. There are multiple locations where the database might be stored in partitions, but those sites are loosely coupled, and a single transaction which wants to access data might access it from one or more sites. So there are two types of distributed databases. First is the homogeneous distributed database, that is, all sites have identical software and appear to the user as a single system. And the other is heterogeneous distributed database. It has that different sites may use different schema and software. So there is a limitation that there might be limited cooperation between different sites due to different schema. So for that, to ensure consistency, we use the two-phase commit protocol. So let's have a look at it. So the two-phase commit protocol is used in distributed databases to ensure consistency in distributed database. So it assumes a fail-stop model. That is, if a system fails, it simply stops working and causes no harm. So let's say we have three sites where T1, T2, and T3, where the database is distributed. And let's say T2 stops working. So it would mean that simply T2 would not respond to any request and it would not cause any other harm, like sending erroneous responses or anything else. So the execution of the protocol is started by the coordinator. The protocol involves all the sites where the transaction is executed, and the protocol is executed in phases as discussed in the next slides. So the two-phase commit protocol has two phases. The first phase is called the prepare to commit phase. It says that the coordinator asks all the participants to prepare to commit the transaction. That means it adds a log record called prepare T to its log, and that log is stored in the stable storage. Next, it sends the prepare T message to all the sites where the transaction has executed. So, what happens then? Upon receiving the prepare message, the transaction manager at a site determines if it can commit the transaction. If it can commit, then it sends the ready T message to the coordinator, saves it to the log, and saves the log to its own stable storage. But if it cannot commit, then it records a no T commit. That is the sorry. That means that it cannot commit the transaction. So it records a no T in the log and sends abort T to the coordinator. Even if the coordinator in the decision next is the decision phase, where even if the coordinator receives one no T from any of the sites, it has to abort the transaction at all sites and the transaction has to be rolled back at all other sites as well. Hence, it is highly desirable to receive a ready T from all the sites. Therefore, we can see that if a coordinator adds a decision record called commit T, then that means that all other sites where the message was sent have sent a ready T. But if it adds abort T, that means at least one site sent a no T message or abort T message. So that was the two-phase commit. But there are several failure modes since it's a distributed environment. So let's have a look at that. The challenges in distributed systems include network issues like partitions, consistency, network latency, and many more are there. But we will discuss about site failures, network partitions, and coordinator failures. So let's first talk about the failure modes. There are that is site failure, network partition, and coordinator failure. So let's have a look at site failure. So let's say a transaction is there where it is executed in multiple locations. Let's say S1, S2, S3, and S4. And let's say S3 fails due to some reason. So when it recovers, it examines its log where the following cases may occur. Like in the log, it contains a commit T or an abort T. That means the transaction had already been completed and is successfully stored in the disk. And if it is contains a ready T, so if a then it has to consult the coordinator. So if a coordinator says that it has entered commit T, that means the transaction would have to redo T and commit T. But if the coordinator says that the transaction was aborted, then undo the operations that were done on T and abort T in the log. But if the log does not contain any entry about prepare tea, then the that means that the site had failed before sending the ready tea reply. That means you have to undo tea in that case. Next, let's move to the coordinator failure. So if a coordinator fails during the 2PC protocol, that means that there can be four cases. Then that means that the other participating sites would have to decide the result of the protocol in the decision phase. That means if any active site contains the result as commit T, then T must have been committed. Therefore, it has to commit all other sites commit. If any site contains abort T, that means T must have been aborted by the coordinator, hence abort T. But if any site does not contain, then it then all the sites would have to wait for the coordinator to recover, and any prepare T messages from the coordinator would have to be ignored until the coordinator has fully recovered. There might be a blocking problem where if the coordinator fails and the remaining sites have to wait for it to recover. That is known as the blocking problem in 2PC, which is generally solved by 3PC, which is beyond the scope of this video. So next we move to handling network partition. Handling network partitions is quite simple actually. It is a combination of coordinator, and the site failure. If the sites in a partition behave as if the coordinator failed, and the site and the coordinator in the first partition behave as if the sites have failed and continue with normal execution. And when the partition is removed, the coordinator adds the remaining sites as well to their own network and the protocol is rerun. So now let's see distributed concurrency control. So, what is concurrency, first of all? Consistency. Consistency means that the, the state of the database before and after remains the consistent. That is, the data is secure and safe, and all the transactions, no matter the order in which they are performed, result in the same final value for all the data items. So there are many approaches like a single lock manager and the distributed lock manager. So in the single lock manager approach, there might be a single point of failure. Hence, we generally prefer distributed lock manager approach, which is also known as Quorum Consensus Protocol. There are many other, but we will discuss about Quorum Consensus Protocol only. So the Quorum Consensus Protocol is used as for maintaining consistency in distributed databases. Therefore, it involves achieving a minimum number of votes from participating sites. Let's say there are n sites, then there must be at least n by 2 votes. For example, there might be other number of votes like n by 3 or n by 4, but generally it is n by 2 for the transaction to be considered valid and to be committed. In all other cases, the transaction would have to be either aborted or wait until it receives the required number of votes. So let's say we have n number of total nodes with their total weights as s. So QR is the read quorum and QW is defined as the write quorum. So the protocol assigns the values of QR and QW such that the following conditions must be met. QR plus QW should be greater than S and QW must be greater than S by 2. This ensures that the consistency is maintained. So, but what does this mean? It means that each read must lock enough replicas or sites that is S that the sum of their heads, that is sigma I equals to 1 to let's say k sites, Si is greater than or equals to QR, that is the read quorum total. And each write must also lock enough weights such that the sum of the weights is greater than QW. But in this protocol, by adjusting the weights, the number of replicas required to be locked can be adjusted. That is either increased or decreased as per the application requirement. So there are many advantages and challenges. Like the advantages are improved consistency, fault tolerant, because not all the systems have to be asked for votes. Let's say we need n votes and one side fails, then we cannot move ahead. But here only n by 2 are required, so we can move ahead and reduce the risk of data conflicts and scalability. Disadvantages may be write bottleneck, deadlocks, increased latency, network dependencies, and there might be some other else as well. So, what is a real world example of QCP? So, a well known database, NoSQL database called Apache Cassandra uses QCP with a quorum of n by 2 plus 1. There are many advantages for this, like tunable consistency, like the consistency rate can be maintained as per the application or user's need. And Cassandra is widely used in many real-world examples and it scales excellently for large-scale applications. Hence, we see that QCP is a scalable protocol as well. There might be deadlock. Let's have a look at deadlocks. There might be deadlocks in QCP as well. For example, let's say there are two sites where with and there are n number of systems, and the quorum says that there is a need for n by 2 plus 1 sites to be for a transaction to have considered valid. Here we see that transaction T1 might have gathered n by 2 votes, and transaction T2 also might have gathered the remaining n by 2 votes. Hence, both T1 and T2 need one vote, but there is no site now that can vote for them. This causes a deadlock, and either T1 or T2 must be rolled back depending on which one is has to be done first to ensure that the deadlock is resolved. So now let's see what is trading consistency for availability. So let's see first what is consistency. So a database has a set of integrity constraints, that is the primary key, foreign key, and etc. There are many other. And a database is said to be consistent if all the integrity constraints are satisfied. But there are only two types of consistency, that is strong consistency and weak consistency. Now let's see what is availability. So high availability means a system is fully usable for maximum duration and the time for which it is not usable is extremely low. That means availability is the time for which the database is usable fully. Therefore, the time taken for the data to be available after the request is made is known as latency. So the real world example for high availability would be Stripe, which is a payment processing company, ensures that its API endpoints are usable and successfully process the requests that arrive at their endpoint. The company ensures and guarantees a 99.999% availability, which is a very good availability as per recent industry standards. So, but in commercial distributed systems, what should we choose out of consistency and availability? So, as we can see, many commercial databases support replication with weak degrees of consistency. It means that the transaction may be executed without guarantee of serializability, and the final state of the database might not be consistent initially. This is done to ensure that the system remains available. Let's say, for example, we have Amazon.com with so Amazon won't prefer that its website is down just for a single due to a single transaction which is taking a long duration of time. Hence, it may allow non-serializability as well, except for the order processing part. So let's see have a look at Brewer's cap theorem. So Brewer's cap theorem says that there are three main properties of a system, that is consistency, availability, and partition tolerance. Brewer's cap theorem also states that we can have at most two of the above three properties for any system. And generally, very large systems like distributed systems tend to have a partition at some point of time or the other. Hence, the system must be partition tolerant. Therefore, we have to select from a consistency and availability. Most traditional systems like banking systems, order processing choose consistency. But for web applications, where we require the data to be available most of the time, we have to choose availability. For example, Amazon, as I said earlier. But to understand the choice between consistency and availability, we must first understand the two types of consistency in detail. So, strong consistency. So, what is strong consistency? It means that consistency is always matter, no matter the effect on availability. So, for example, many a times we have seen that the bank server is down. This happens because some transactions are being executed which have to be completed before the users can be served. Hence, that is the case of strong consistency. And let's say next is weak consistency. Therefore, in this, we sometimes have to let go of consistency for a very short duration to make the data available. As in the case of Amazon, as I said earlier, if some user is making a payment and is taking a long time, the other users don't have to wait for the data. All the for the website to load, the all the website is always up. That means we can have replication with weak consistency. For that, we have to modify the QCP protocol, which we discussed earlier, as follows, where the read and the write quorum total sum can be less than the sum of the weights required, and QW can be less than S by 2. The effects may be that writes may occur in parallel, leading to inconsistent versions, and the reads may get older versions of the data. Let's say, for example, a transaction T1 writes the data and T2 has to read the data after T1 has written. But in this case, T2 might read the data before and might get a older data before even T2 has written. T1 has written the data. Most systems which choose availability ensure that there will be eventual consistency. That means that all the updates that have been done would eventually propagate to all the nodes and the database would become consistent again. Such databases follow base properties instead of ACID properties. But what are base properties? It basically stands for basically available, soft state, and eventual consistency. The database is available for most of the time. Soft state means that copies of data may be inconsistent. Eventual consistency means that all copies become consistent at some point of time later when the number of transactions is less. So, but what difference between base and acid properties? So in case of base properties, they ensure that eventually consistency is achieved and they support weak consistency only. On the other hand, acid properties ensure that the database always remains consistent no matter the effect on availability and they always support strong consistency only. Some real world examples which use base properties are Apache Cassandra, as discussed earlier, Amazon DynamoDB, Couchbase, and MongoDB. The last two and the first one being the a NoSQL database. So there might be some cases where the chances of partitions are very less. For such systems, can we go let go of consistency for availability? Is there a need to select partition tolerance even if the chances of partition are less? If a system chooses consistency, the transaction processing may increase the time taken for responding to the transaction. Hence, system may have to trade off consistency for latency in this case as well to reduce the latency. That is the response time for the user. Let's say I click on a product on Amazon, it takes an hour to load. I won't be buying from Amazon. But if the site loads instantly, I would prefer buying from there because the user experience improves greatly in that case. So we have arrived at the conclusion that when we require the data to be available for and with low latency, then consistency has to be traded off in some case or the other. For example, in e-commerce application where monetary transactions or order processing are not taken care of, like the loading of a website and all other cases. But if we want that data remains accurate and the database remains consistent each and every time any transaction is done, for example, in banking applications, then we have to go for consistency and leave out availability. So that would be the breakdown for this video, and thank you very much.